Okay, so I think we can start now. So, very good evening to all of you. I'm Anirudh, a BSc second year student at CMI. Firstly, a huge thanks to all of you for attending this lecture organized by STEMs of CMI. So today we have with us Professor Ved Datar from the Indian Institute of Science, Bangalore. Professor Ved obtained his bachelor's in mathematics and computer science from Chennai Mathematical Institute and went on to pursue his PhD from Rutgers under the guidance of Professor Jeon Song. And his primary interests include geometric analysis and complex differential geometry. And Professor Datar has a lot of credentials to his name, one of which includes he was recently awarded the Infosys Young Investigator Award in 2019 of August, and for his contributions towards the subject of math. A couple of quick instructions before I hand it over to Professor Ved. Please use the chat box for your questions, and we'll post them to Professor Datar as and when the time is appropriate. Today, Professor Datar will widen your imagination by asking a simple yet interesting to answer question. Should all the angles in a triangle sum to 180 degrees? So I hope all of you enjoy. Over to you, sir.
Right. Thanks for the introduction, and I would like to thank the organizers for this opportunity. So as was mentioned, I'll talk about this very basic sum angle property that we learn about in high school. I guess I think in my time, not that I'm that old, but in our time, this used to be taught, I think, in the 8th standard. And so the goal will actually be to start with that, but then sort of move on to describe some bit of geometry of curves and surfaces, and the eventual goal would be to sort of try to describe this one piece of this relationship between topology and geometry. These two are important fields in modern mathematics, and it's quite incredible that sort of story begins about, I don't know, 2000 years back to this simple sum angle property of triangles. Okay, so before I move on to geometry, let me first, at the outset, sort of describe some basic differences between topology and geometry. So topology and geometry both are study of shapes, but the difference is that in topology, we are allowed to sort of deform shapes in a continuous manner without introducing any tears, etc. And so that's why it's sometimes called, very suggestively, it's called rubber sheet geometry. And so in the realm of topology, a donut, which in fancier language is called the torus, is basically the same as a coffee mug, which is closed off, right? So this is supposed to be the lid of the coffee mug. And you can, of course, imagine that if the coffee mug were not to be made of glass, but let's say it was a clay coffee mug, then you could easily, or rather a rubber coffee mug, you could easily change that into a donut. On the other hand, in geometry, we actually keep track of distances and angles. So in geometry, whenever you want to deform an object, you need to preserve distances and angles. Okay, so then clearly the donut is not the same object as the coffee mug, right? All right, so now let me go back to the sum angle property. So of course, what that says is that the sum of interior angles of a triangle in a plane always equals pi. So of course, I'll use pi and 180 degrees interchangeably. So it's I mean, in mathematics, it's more convenient to work with pi instead of degrees. So work with radians instead of degrees. Right, so I've drawn a triangle here. Now, how do you prove the sum angle property? Well, the proof is quite simple. All you do is you basically this parallel line, and then of course by the alternate angle property. Sorry, I should right. So by the alternate angle property, this angle is alpha, this angle is also beta, and together alpha, beta, gamma make up a straight line. So clearly alpha plus beta plus gamma is equal to the angle on a straight line, which is pi. Right. So another way of saying the same thing is, instead of looking at the interior angles, I look at the external angles, and this later on will turn out to be more convenient. So as far as external angles go, you basically look at these angles, right? And then clearly the sum of angles will be 2 pi, right? Okay, so that brings us to sort of two basic questions. Firstly, is this true for other geometries? So what do I mean by other geometries? So for the purposes of this talk, when I say other geometries, I'm going to actually restrict attention to surfaces in 3 dimensions. Okay, so that means whenever I say distances, you're basically, I mean, you should imagine being an ant on that surface that you're looking at, and you can only move around on that surface. So you should forget about the 3-dimensional world around you. You're allowed only to move on that surface. And so then the distances have to be measured along that surface, right? So of course, this is similar. I mean, we don't need to think of an ant. This is similar to us on the earth, right? I mean, the distances that we measure out from, let's say I'm sitting in Bangalore to Mumbai, are basically along the surface of the earth, right? So, right. So whenever I say geometry, I'll basically mean that my world is now a surface and I'm measuring distances and angles on that surface. And so a natural question is, what is a triangle, right? I mean, in a plane, a triangle is basically a figure which has 3 vertices, which are now connected by straight lines, right? So that means we have to really understand what should replace straight lines in, I mean, once our world becomes a surface, what should replace straight lines? And the other point is something that I'll not spend a lot of time on, is a crucial part in this proof is played by, drawing a parallel line. And this somehow uses this very famous parallel postulate of Euclid, famous and controversial. And of course, a natural question to ask is if the parallel postulate is valid in other geometries. And in fact, the fact that people were questioning the parallel postulate, this actually led people to invent new geometries. Okay. All right. So let me start with a very basic example. Let's consider this triangle on the sphere. So I basically have the North Pole here, and this guy is the equator, and I choose 2 points A and B on the equator so that the corresponding longitudes are basically 90 degrees off from each other, or pi by 2 off from each other. Right. So by any conceivable notion, this would probably be a good definition for a triangle, right? So of course, in a plane, a triangle is made up of 3 straight lines. So once you're on a circle, what should replace straight line? Well, that should just be the great circles, right? So imagine if you're supposed to travel from the North Pole all the way to the South Pole, what would be the shortest way of getting to the South Pole? Of course, it would be by following one of the longitudes, right? So similarly, the sphere is nice and symmetric. So if you're at any point, you can always rotate so that you come back to the North Pole. And then to get to any other point, of course, the best way is to travel along a longitude, right? So that's the shortest way. And in fact, if you're living on that sphere, the shortest way would seem like a straight line to you, right? So for instance, our experience with flights is that it's always best to not take the straight line path on the map, but to actually take these great circles up to some approximation of wind conditions and so on, right? So so this ABN can legitimately be called a triangle on a sphere. So I'll call it a spherical triangle. And then clearly we see that the sum of angles is actually 3 pi by 2, right? Because it has 90 degrees at each vertex. So that's bigger than pi. So you have already found an example of something that you can legitimately call a triangle and whose sum of angles turns out to be bigger than pi. And by how much? It turns out to be bigger than pi by what I'll call the angle defect, which is pi by 2. Right. So now let me do something which might appear a bit strange right now, but let me try to calculate the area of this of this triangle. So of course, you can imagine that if you, you can imagine this sphere being a lemon, and you're basically cutting out 1/8 of the lemon, right? Because the angle here is pi by 2. So if you go around, you would be basically you'd be able to make 4 such slices, and then of course that would slice up the upper hemisphere, but you also have the lower hemisphere. So if you do the same thing to the lower hemisphere, you would end up with 8 regions. So of course the area of one region is 1/8 the sphere. And what is the area of the sphere? So all my spheres today are going to have just unit radius, right? So the radius is going to be 1. So what is the area of the sphere? It's simply 4 pi. So this is going to be pi by 2. So you see that this number, the area of this triangle, seems to be the same as the angle defect, right? So is this a coincidence? It turns out that it's not a coincidence. So I'll state a theorem in a minute. And the theorem will be about spherical triangles. So these are triangles whose sides, as I said, are made up of straight lines on the circle. Straight lines on the circles are basically parts of these great circles, right? Okay, so then the theorem reads that if you have one such spherical triangle, so I've drawn it out here. Then if you take the sum of angles, that turns out to be precisely plus of the triangle. Okay, so how do you prove this? So the way to prove this is to note these regions S alpha 1 and S alpha 2. So let me color these regions. So it's basically so you have this angle alpha, and that goes behind on the sphere, and you'd get this region, right? Right. So that's the region S alpha 1. So I should also say that I should mention that whenever you have such a spherical triangle, you can always project it onto something that's diametrically opposite, and you basically end up with another sort of mirror image of this triangle, which I've denoted by A prime, B prime, C prime, right? So now, similar to this region S alpha 1, you also have a region here, which I'll call as S alpha 2. And of course, there's also the region that goes behind the sphere, which I'll color with a slightly, sorry, my coloring has gone wrong. Right, so this is the great circle. So yeah. So what is the area of S alpha 1 plus the area of S alpha 2? Okay, so how do you calculate that? Well, you can imagine that if you let this alpha become bigger and go all the way up to pi, then you can imagine covering up the entire sphere, right? So if the angle is pi, you would cover up the entire sphere. So if the angle is alpha, you would basically cover up 4 alpha worth of area. Right. So similarly, I can do the same thing, but to these other angles, beta and gamma. So for beta, for instance, I look at this region. And similarly, I have a formula that area of S beta 1 plus area of S beta 2 is 4 beta. And similarly, area of S gamma 1 plus area of S gamma 2 is 4 gamma. Now together, clearly this covers up the entire sphere, right? On the other hand, if you notice your sort of triangle and its mirror image, then in each of these, the triangle and the mirror image appear once each, right? And of course, the triangle and its mirror image have the same area. So that means you're actually counting the area of the triangle, which you should count twice. I mean, once for the triangle and once for its mirror image. You're actually now counting it 6 times. So that means if you add up all these areas, you would of course get the area of the whole square, plus you would get 4 times the area of the triangle. Okay, but then of course, if you cancel out 4, so if you cancel out 4, you basically end up with precisely this, right? So that proves the sum angle property for spherical triangles. Okay, so let me talk a bit about some couple of simple consequences. So firstly, this tells you that spherical geometry is actually very different from Euclidean geometry, right? Because remember, in Euclidean geometry, you have all these similar triangles which have the same interior angles, but of course the size could be really large. On the other hand, for spherical triangles, this actually tells you that if you have the same angles, then the area also must be the same, right? So the sum of angles is the same, the area must be the same. So on the sphere, you can't really scale up triangles, keeping the angles the same, right? So this also tells us that the Earth is not flat. So the geometry on the Earth is different from the geometry of the plane, and it also tells us that one cannot have accurate maps, right? Because the point is that if you had by accurate maps, I mean maps that preserve distances. If you had accurate maps, then of course spherical triangles would be like ordinary triangles on the map, and then the sum angle property would be the same as in Euclidean or plane geometry, right? But we have already found out that there's a different sum angle property on a sphere. So actually, this is quite amusing to look at the map of. Look at the map of the world, and you'll actually find that Greenland is almost the same size as Africa, whereas in reality, Africa is about 14 times bigger in area than Greenland, right? So, simple sort of geometry tells you that you cannot actually have a distance preserving map of the globe, right? Okay, so now I want to do something slightly fancier. So in high school, we only deal with triangles whose edges are straight lines, right? So whose sides are straight lines. But now I want to do something fancier than that. I want to allow curved sides for my triangle, right? So here I've drawn 2 examples. So it's best to actually imagine this triangle as basically a racetrack on which maybe you're driving a car. So clearly, if I label the exterior angles as epsilon1 or E1, E2, E3, then it's apparent that for this triangle on the left, the exterior angles seem to be bigger than that of a regular triangle, right? Because for a regular triangle, sorry, I should not erase that. For a regular triangle, you would actually connect these 2 points by a straight line, and then at both ends, you see that the exterior angle here seems to be bigger. So you would actually expect that the sum of exterior angles for this sort of curved triangle is actually bigger than 2 pi. Okay, so I want to right. So I want to say something else about this. So let's notice. Suppose you're going from A3 to A1. So all along from A3 to A1, you're traveling on a very smooth curve, and suddenly, as soon as you come to A1, you have to suddenly change your direction, right? So that means your velocity vector has to suddenly change from this direction to this direction. Similarly, you go along all nice and smoothly up to A2, and again, suddenly your sort of velocity vector has to change. Now, suppose you had traveled on the straight line, the velocity vector at the initial point here would be the same as the velocity vector here until you're forced to sort of abruptly change. On the other hand, for the curved triangle, you notice that, so I've extended the velocity vectors here. You notice that they actually make an angle, right? And so I'll call this angle θ12. And the convention is that if your angle turns sort of clockwise, you call it a negative angle. And if the angle turns anti-clockwise, you call it the positive angle. So for the triangle on the left, all the angles would be negative, right? On the other hand, for the fat triangle, you can do a similar sort of thing, and you would notice that firstly, you would expect that the sum of angles would be less than 2 pi. And all these turning angles, so I've drawn the θ12 here, they would now turn anti-clockwise. So by our convention, they would be positive, okay? All right, so now the sum angle property here takes the following form. So if you add up all the external angles, then it turns out that it's 2 pi minus the total rotation angle. Oh, so I should, sorry, my convention has, right. So yeah, it's 2 pi minus the total rotation angle. So for the first case, all the rotation angles are basically negative. So if you add up the total rotation angle, that would be negative. You're subtracting something negative. So the external angles add up to be more than 2 pi. And the opposite happens for the fat triangle. Okay, so the Gauss-Bonnet theorem basically generalizes both these situations. So remember, the sum angle property that we learned in high school was for straight lines, whereas this property that I've just now told you is which also works for curved, for curved triangles. And of course, if you have a straight triangle, then this total rotation angle would be 0, and you'd recover the property that you learn in high school. So the Gauss-Bonnet actually generalizes all of that. So I'll first state the Gauss-Bonnet, and it will have lots of terms that make no sense to you. But for the entirety of the lecture, I'll basically, my goal will be to describe what these terms are, right? What these mysterious terms are. So for Gauss-Bonnet, I actually want to generalize even further. Instead of triangles, I actually want to look at polygons, right? And I want to look at simple polygons, which just means that there's no hole inside the polygon. So S is going to be my surface. So you can, if you're comfortable, you can just, or rather, if you're uncomfortable, you can just imagine the surface of a sphere. But it could be an abstract surface. It could be the surface of a paraboloid or an ellipsoid, whatever. And then I choose a polygon on that. And you can see that I've marked out all the external angles. So what the local Gauss-Bonnet tells you is that it tells you exactly what the sum total of the external angles is going to be. That's going to be 2 pi minus some correction terms. And there are two correction terms that come up. Firstly, you will need the total turning angle. So essentially what that means is when we had a curved triangle on a plane, one could, right. So the point here is that, let's zoom in on this. So for each point on one of the sides, you're basically going to sort of, at that instant, your velocity vector is going to turn. And you want to calculate at each instant what is the instantaneous turning angle, and then you basically add up all of these contributions, right? So that is essentially what is meant by integration, by this symbol. So for if there is somebody in the audience from high school, it doesn't matter if you haven't seen integration, what that means is that you're basically adding up those little instantaneous sort of turning contributions all the way along the side. And similarly, for the second term, you basically take a point inside the polygon, and you're no longer on a plane, so your surface might be curving, and this basically takes care of the contribution from that curving of your surface. So again, you basically take the what is called as the curvature at each of those points and add up to get a sum total of that, and that is basically what this term means, right? Okay, so now for the next maybe 15 minutes, I'm basically going to describe how to calculate these two quantities. Okay, so of course, intuitively I've told you what these mean, but they're not useful unless you can actually sit down and calculate. In real life situations, you should be able to sit down and calculate, right? Okay, so I should just make a remark quickly that if you go back to the previous settings, namely spherical triangle and sort of curved triangles on the plane, you'd basically recover these statements that I wrote down. Okay. All right. So now let's talk about this. I mean, my aim is to talk about this object KG. So the simplest curve is, of course, a circle. So let's first talk about circles. So imagine you're on again a racetrack. I mean, this is supposed to be a car. Probably a very bad drawing, but this is supposed to be a car. And let's say you travel from this point A to point B. You want to measure how much your velocity vector has actually turned, what angle it has turned, right? So let me remind you of something from, before I get to calculating that turning angle, let me remind you something from high school physics, that if you're traveling at a constant speed, so throughout the entire talk, I'll always travel at, I'll be very boring and always travel at constant speed, okay, which you can take to be your favorite speed. I'll take it to be the average sort of 1 kilometer per minute, so 60 kilometer per hour, right? So let's say we always travel with constant speed. Then high school physics tells you that there is this acceleration towards the center of the track, right? Of course, there's no acceleration in the tangential direction because your speed is constant, right? So, but there is an acceleration in the central direction, and the magnitude of that acceleration is precisely 1 over r, right? Because it's normally v squared over r, but my speed is 1, so the acceleration is 1 over r, right? So now let's try to calculate this turning angle. It's quite clear because tangents make 90 degrees with all the radii. It's clear that the turning angle from A to B is precisely this theta AB, which is the central angle that this sector subtends at the center, right? And so I want to write this as the following. So let me not make a mess of this. Just one sec. Right. So I want to write it as this. Right. So I'm just multiplying and dividing by the radius. But now if you notice, what is this term? This is precisely the arc length as you travel from the point A to point B, right? So remember, my kg was basically the sort of instantaneous turning of, or a measure of the instantaneous turning of the angle. So over a distance traveled, which is equal to theta times r, I'm turning an angle of theta. So what is the instantaneous change of angle? That's basically 1 over r. Okay, so in this case, in this very simple setting, the turning angle is basically 1 over the radius. Okay, so now let's look at general surfaces in 3 dimensions. So of course, it's harder to draw pictures because I'm drawing a picture on two dimensions. But now before I go on to sort of curvature of curves, let me describe a simple problem. Suppose S is our surface. And let's say I want to travel from the point A to point B, right? So what is the shortest path between these 2 points? Okay, so again, I'm traveling at unit speed. So basically, I would like to reach B the fastest, right? So of course, you can draw multiple paths between A and B, which are not optimal. And then you would have sort of at least one optimal path between A and B, which would be the shortest. So this would be the shortest path. Okay, so you should think of straight lines when your entire world is now a surface. You should think of straight lines as sort of the shortest paths between 2 points, right? And again, your experience of living on the earth is that if you actually travel along a great circle, because you're sort of living on this spherical surface, you would actually think that you're traveling in a straight line, right? If somebody didn't come from outer space and actually told you that you're actually traveling in a curved path in 3-dimensional space, for you, that path would just be a straight line. So the analogs of straight lines when we are working on surfaces are basically these sort of cheapest ways of going from one point to the other. Okay, so here's a picture of a surface, and I've drawn this plane. This plane is called the tangent plane. So what it does is it sort of just touches your surface at that point, and it's a plane, so one can do more with it than one can with curved surfaces. So the idea is that this plane, at least locally near that point, is a reasonably good approximation to your surface. Okay, so now what is the velocity? Let me remind you what velocity is from high school physics. This is basically the rate of change of displacement, right? So as you're moving along this, your rate of change of displacement, that's a vector. Velocity is not just a number, it's a number and a direction. And that is going to be the rate of change of your displacement. The acceleration is basically going to be a rate of change of the velocity. Okay, now suppose you're traveling with a constant speed. It's a good exercise for those of you who know a bit of vector algebra. It's a good exercise that the acceleration vector is always going to be perpendicular to the velocity vector if you're traveling at constant speed. Okay. So then it's quite clear from the picture that if you travel along the shortest path, this implies that your acceleration vector is actually perpendicular to not only the velocity vector, but to the surface itself. Right? Why is that? Because so let's in this figure, let's draw the acceleration vector. It's something perpendicular to let's say the velocity vector. And the tangent plane has another vector that is perpendicular to the velocity vector. So let's draw that with maybe a yellow line. Oh, so this, right. So maybe let me draw a better picture. Right. So let's say this is another thing perpendicular to the velocity and the acceleration. Now imagine the acceleration vector. You know that it's perpendicular to the velocity vector, but there are 3 perpendicular directions, right? The acceleration vector, the velocity vector, and then this blue perpendicular direction. So your acceleration might have some component along the perpendicular direction, but you can imagine that if it has some component along the perpendicular direction, then at least locally, your path would tend to go a bit in that direction, which would mean that you would actually end up wasting some fuel in getting from A to B. right? So at least intuitively, it's clear that if you're on the shortest path, then the acceleration should actually be perpendicular, not just to the velocity, but to the entire surface. Because otherwise you could, at least to second order, you could travel slightly in the direction of that extra perpendicular direction, and you would end up wasting time getting from A to B, right? So you no longer be on the shortest path. Okay, so an example is on a sphere. These are basically great circles. On the other hand, on a cylinder, there are actually two types of curves. So you can, of course, imagine this point. I mean, on a cylinder, you can imagine this circle. On the other hand, if you have a point, let's say here, how do you get from A to, let's say, B? Well, the way to get to that is to travel along a path that looks like this. Right, so it's actually a helix. And how do you show this rigorously? Well, it turns out that to measure distances on the cylinder, what you can do is you can basically cut the cylinder along one of its vertical axis, and you can spread out the cylinder. And it turns out that this process actually preserves distances. So now the spread out thing is on a plane. On a plane, you know that the shortest distances are given by straight lines. And so you basically just travel by straight lines. So the analog of the point B would be here. You just travel along from A to B on a straight line. And once you roll up your cylinder, that will basically give you a helix. So straight line paths on cylinders are basically these circles or these helices. And there is, of course, a third one. You can, of course, go also vertically. Right, so there are these three types of straight line paths on a cylinder. Okay, so what about curvature of curves in 3D? I said something about curvature or bending of curves in 2D, and I said that had something to do with the magnitude of the acceleration. Again, speed is constant, so I said that had something to do with magnitude of the acceleration. So now, in 3 dimensions, remember the speed is constant, so the acceleration vector is perpendicular to the velocity vector. So actually, there's a mistake here. Sorry. So let's say I focus on this point P. There are 3 perpendicular directions that I can talk about. One is the velocity direction. The other one, so you should imagine being on this, traveling on this circle. So the acceleration will point towards the center of that circle, right? Not the sphere, the center of that circle. So that's the green vector. But there's this additional perpendicular direction to the velocity, which basically goes upwards along. So, it goes almost in a longitudinal direction, right? So you're traveling along the circle. There is another perpendicular direction that I call as S. So the acceleration vector is perpendicular to the velocity vector. So it has, it can have 3 components, but because it's perpendicular to the velocity vector, that component is 0. So it has these 2 components, which I'll, which I'll write as kg and kn. So this normal is the inward pointing normal to the sphere, and the inward pointing normal is, of course, towards the center of the sphere, right? So that's this n. And so I can decompose the acceleration into a component along S, a component along n, and I define the normal curvature as the component along n. I define the geodesic curvature as the curvature along G. Okay, so now remember I said that a geodesic, or the shortest path, is basically when the acceleration vector is perpendicular to the surface. So that means in that case, let's say you're working on a great circle, the acceleration vector will not have any component along S direction. So a geodesic or a straight line implies that the geodesic curvature is going to be 0. That's why this component is called the geodesic curvature. So the geodesic curvature is 0 when you're on a straight line. Okay. All right. So that is all about curvature of curves. Remember, in the Gauss-Bonnet, there was another term which was in green, which was basically the what is called the Gauss curvature. So let me remind you, we had this additional term, right? So now let me take maybe 5 minutes to describe this additional term. Right. So so the Gauss curvature is simply so let's say I'm trying to calculate the curvature at this point P. What I do is simply take all possible curves passing through this point, right? So maybe I should have used slightly different colors. Right. So you can imagine, let's say I draw this first curve in green, and you can imagine drawing another curve which goes something like this, right? And then comes out from behind. So I take all possible curves and I calculate the maximum possible normal curvature. I call that K2. I compute the minimum possible normal curvature. I call that K1. And the Gauss curvature is defined to be the product of these two. Okay, so this might seem like a very strange thing to do. Why do you multiply these two things together? For people who have learned a bit of linear algebra, what is really happening is that K1, K2 turn out to be what are called as eigenvectors of the shape operator, whatever that is. Okay, and then of course the Gauss curvature is like the determinant of that shape operator. The shape operator in a suitable basis is given by a matrix. The Gauss curvature is like the determinant of that. And the reason you take the determinant is essentially if you're given a 2x2 matrix, there are essentially only two invariants. You can either add up the two eigenvalues or you can multiply them. By adding up, you get what is called as the mean curvature. But the mean curvature, it turns out, is not an intrinsic quantity. Okay, so it turns out that the Gauss curvature actually is more of an intrinsic quantity. So it will take probably another hour to just tell you more about the Gauss curvature. So maybe I'll leave it at this mysterious looking definition. But maybe it's good to look at a few examples, right? So let's look at the simplest example, that of a sphere. So for a sphere, firstly, when you're computing this Gauss curvature, because you're looking at only normal curvatures, it's actually enough to look at sort of these local straight lines near that point, right? Because I mean, the acceleration component is going to be divided between the normal part and the geodesic part. So clearly the normal part for things that are not straight lines is going to be smaller or larger than the minimum quantity and smaller than the maximum quantity, right? So it's best to just look at all possible straight line paths. So on a sphere, all possible straight line paths, it's actually quite easy to calculate that the normal curvature will be just 1. I'm looking at a sphere of radius 1, so the normal curvature will just be 1. On the other hand, on a cylinder, what happens is the following. So if you have these two types of curves which maximize maximize and minimize respectively the normal curvatures. The first one that maximizes it is basically given by these these circular straight line paths, and the minimum is actually given by this vertical straight line. Okay, so it turns out that the minimum, you can clearly see that this line is actually not bending at all. So the minimum turns out to be 0. The maximum, let's say you're working on a cylinder of radius 1, the maximum turns out to be 1. So their product is 0. So the curvature of a cylinder is actually 0, which is quite, I mean, if you think about it, it might be a bit surprising because, I mean, when you look at a cylinder, the cylinder is actually bending, right? And yet here we are saying that its curvature is actually 0. But you should remember this picture that I drew, that you can actually cut open a cylinder and lay it out on the flat plane. And all the distances, etc., are preserved. So all the geometry is actually preserved by doing this sort of cutting and putting it down on a plane. So that should explain why this is a reasonable answer, that the curvature is actually 0 for a cylinder. Okay. All right. Now, how does a negative curvature thing look like? Well, the standard example is that of a saddle. And so I've drawn two possible curves here. So, and I'm taking a normal direction, which is sort of inside, pointing into the surface. So now if you look at the green curve, clearly the acceleration there is pointing towards the normal, right? So the maximum normal curvature is clearly going to be positive. The component of the acceleration along this curve is going to be positive. On the other hand, if you take this curve, yeah.
That was just tracer. Sorry for that.
Sorry, is there a question?
No. That was just a tracer. Sorry.
I see. Okay, so if you take the other curve, then you'll see that the acceleration actually points opposite to the normal. So the minimum is actually going to be negative. And so the Gauss curvature of a saddle is going to be negative. Okay, so one place where you sort of see these saddles is, of course, if you've gone hiking, as soon as you come to a mountain pass, that basically looks like a saddle. Or you can look at the donut. Now, if you look at the inside part of the donut, so I've again drawn these two curves. Clearly, the inside part has negative curvature. On the other hand, the outside portion actually looks almost locally like a sphere, right? So the Gauss curvature here is going to be positive. So on a donut, you have points that are of negative curvature, you have points that are of positive curvature. And so now let me again remind you of the local Gauss-Bonnet. It says that the sum total of the external angles is 2 pi minus these two correction terms. The first one involves the geodesic curvature. So remember, the geodesic curvature will actually be 0 if your polygon consists of straight lines, right? So straight lines on the surface. On the other hand, you also have a second correction term that comes about because your surface itself is curved. So not only are your curves curved, I mean, you can do away with the second term by choosing straight line paths, but your surface itself is curved. So you cannot really do away with the second correction term. Okay. So I hope now all of you understand the Gauss-Bonnet. So in the next maybe 5 to 10 remaining minutes, let me sort of switch subjects completely, and so I mean, all of this was quite, I'm sure, quite heavy. I mean, especially if you haven't dealt with vectors, this might appear quite scary. But now let's again go back to something that's extremely elementary, that any high school student in 5th or 6th grade can actually understand. So there's this famous Euler formula. So suppose you take a simple convex polyhedron. So I've drawn a picture here of a dodecahedron. And you do the following: you count the number of vertices, you count the number of edges, and you count the number of faces, and you take this alternating sum. And magically, it turns out that this alternating sum is always equal to 2. It doesn't matter what polyhedron you choose, you'll always end up with 2. Okay, so the number of vertices may be extremely large, the number of faces might be very different, etc. But once you take this alternating sum, you'll always end up with 2. Okay, so in this picture that I've drawn, the vertices are 20, the edges are 30, and the faces are 12. So if you calculate this will turn out to be, hopefully I have this correct. Right, so that's 32 minus 30, so that's 2. Okay. All right. So there are a couple of simple consequences of this. Firstly, you can think of this sort of polyhedron that I've drawn as maybe a football that's not completely inflated out, right? But now suppose you inflate the football all the way till the extent that which you can inflate it, then of course this this polyhedron will basically turn into a very nice round ball. And so you can actually imagine this polyhedron as actually polygonal decomposition of the sphere, right? So I mean, if you look at a nice round football, you of course see these sort of hexagons and pentagons that decompose your ball, right? Or the surface of your ball. So another way of thinking of this Euler formula is, instead of thinking of polyhedrons in R3, which are simple and convex, you can actually think of polygonal decompositions of the sphere. And then, of course, you count the number of vertices, edges, faces. You do this alternating sum, you always end up with 2. Okay. And in fact, this is an extremely powerful invariant. So invariants are always extremely useful in mathematics. So whenever you find an invariant, that is likely to be a rather deep discovery. So for instance, one application of this is that you can prove that there are only 5 convex regular polyhedrons, right? So when I say regular, that means that each face of the polyhedron ought to be a regular polygon, and you can sort of not rearrange, but you could deform it so that each of the vertices lies on the sphere, right? And so then there is a theorem which is very classical. It says that there are only 5 convex regular polyhedrons. This is markedly, I mean, different from what happens in the plane, right? In the plane, you can draw as many regular polygons as you want, right? There are infinite number of them. But in 3 dimensions, there is this rigidity that you can only have 5 of them. And this is actually a good sort of competition math problem to actually take the Euler formula and to deduce that you can only have 5 convex regular polyhedrons. So it turns out that you'll have to solve a certain, not quite a Diophantine, or yeah, you can call it a Diophantine equation. Okay, so you can take that as an exercise. And another thing to notice is that, suppose, again, you imagine your sort of polyhedron as being a football, which is not inflated all the way along. Now, suppose you deform it continuously. Clearly, the number of vertices, number of edges, number of faces is not going to change, right? So clearly, this number 2 is invariant of deforming the sphere. So you can deform the sphere into some very weird looking object, as long as you don't introduce any tears. So again, think of the sphere as either a football or a balloon, and you sort of squeeze the balloon in various directions, but you don't burst the balloon, right? And then whatever shape you get, whatever surface you get, you do this polygonal decomposition, and the number is again going to turn out to be 2. So that's obvious, right? Because these numbers don't really depend on, I mean, they remain unchanged even if you continuously deform your surface. Okay, so now the important thing here is that we are looking at simple polyhedrons, which means polyhedrons without a hole. So what happens if we introduce a hole? So for that, maybe I'll quickly talk about closed surfaces in 3 dimensions. So a caution is that all our surfaces are going to be 2-sided. So I don't want to deal with the Mobius strip, right? Or things like the Mobius strip. So of course there is, whatever I talk about, there is an equivalent version also for these so-called one-sided surfaces, but I don't want to deal with that right now. So I'm also going to only look at closed surfaces. So closed surfaces means that there is going to be no edge. So there's not going to be any edge that you can fall off from. So this was the great fear of our ancestors, right? That the earth has an edge that one might fall off from. So I don't want to consider such surfaces. I only want to consider surfaces where you can't fall off from an edge. And then I say that 2 surfaces are topologically same if I said this in the introduction, if they can be changed into one another by a continuous sort of rubber sheet deformation. Okay, so that means, for instance, a donut is not the same as a sphere, because the donut has a hole, but a sphere does not have a hole, and there's no way, unless you tear into the rubber, there's no way to introduce a hole, right? Just by sort of continuously deforming the rubber. So this is not the same as this. On the other hand, the cup is the same as the donut. And in fact, you can think of the cup as basically just a sphere with an additional handle. Okay, so this turns out to be a very useful perspective. And in fact, there's a classification of closed surfaces in 3 dimensions, that all closed surfaces are basically given by attaching handles to spheres. And the number of handles that you add is called the genus, and it's denoted by G. Okay, so for instance, the donut is a sphere with 1 handle. A 2-hole donut is a sphere with 2 handles, and so on, right? So then the Euler theorem for such surfaces actually says that if you calculate this alternating sum, again, you have to add a correction factor, and the correction factor is precisely you have to subtract off 2 times the number of holes. Okay, so that's the Euler theorem for a closed surface. Okay, so that finally brings us to the punchline for this talk. In that, if S is a closed surface with G handles, then it turns out that if you compute the total, so if you compute the total curvature, that is precisely going to be 2 pi times this Euler number that you get, which is 2 minus 2g. Okay, so no matter, so this is quite a remarkable formula, because on the right hand side you have something that's a geometric quantity. On the other hand, on the left hand side you have something that's a topological quantity, which remains unchanged under deformations, right? So for instance, if you look at a donut where the genus is 1, so the right hand side will become 0. So the Gauss-Bonnet actually tells you that the integral of the total curvature is 0. Now, I already pointed out that on the inner parts of the torus, the curvature is negative. On the outer parts, the curvature is positive. So in fact, the Gauss-Bonnet tells you that the curvature has distributed itself so beautifully that the positive parts precisely cancel out with the negative parts on a donut. Okay. Similarly, if you take a sphere, for instance, you can continuously deform a sphere into this weird looking object. So of course, the distances on this weird looking object are very different from distances on a sphere. But Gauss-Bonnet tells you that the total curvature will still be 4 pi. So now when you have, remember, a sphere is sort of uniformly curved. When you have introduced this deformation, you have maybe added sort of things that are peaks where the curvature is going to be really large and positive, and you might have valleys where the curvature might be negative, right? But what this says is that it will again redistribute itself so beautifully that the total curvature will remain unchanged. It will always be 4 pi. Okay. And another thing to note is that this is actually independent of size. So it doesn't matter whether you are working, whether your sphere is the earth or your sphere is the ball, is your football, right? The right hand side will always be 4 pi. It's independent of the size. Now, if you think about it a bit, that's not totally surprising, because, for instance, if you take the earth, for instance, the curvature of the earth is positive, but it's quite small. And that is why many of our ancestors were fooled into believing that we are actually living on a flat surface, right? And of course, there are also delusional flat earthers that still believe that we are living on a flat world. But that's sort of reasonable, because locally your earth is very close to being flat because the curvature is very small. On the other hand, the area is quite big, right? So that is what compensates for the smallness of the curvature in this integral. On the other hand, if you're looking at a small ball, the curvature is really large, but the area is small. And in fact, the area goes precisely like r squared, where r is the radius, and the Gauss curvature precisely goes like 1 by r squared. So when you take the total contribution, it cancels out and it's independent of the size, at least for the sphere, right? Okay, so maybe I'll end here. So as an exercise, you should, so maybe I'll leave this as an exercise. I intended to do at least the outline of the proof, but maybe I'll leave this as an exercise. So use local Gauss-Bonnet plus the Euler formula to prove the global Gauss-Bonnet. Okay, so it's basically like a counting problem. So the idea is that you triangulate your surface, and then on each triangle you apply the local Gauss-Bonnet and do a very careful counting. That's essentially the proof. Okay, so maybe I'll stop here. Thanks.
Wow, thank you very much. So that was indeed like exceptionally presented. Like this has indeed like raised quite a few thoughts. So a couple of okay, so a couple of questions which are already in the chats. Maybe chats questions as well as observations. So does that mean a torus-shaped Earth can have an accurate flat map?
Yeah, that's a good question, and the answer is yes, it can. Yeah. Not the torus that we see. So I should clarify. Sorry. The torus that we or the donut that we see is actually a donut in R3, right? So it's a donut in R3. So if you take a donut in R3, you can measure distances on that, and you cannot accurately represent it on a flat surface. Why? Because there are regions of positive curvature, there are regions of negative curvature. So if you take, for instance, small triangles near regions of positive curvature, you'd have the same problem that you have with triangles on the sphere, right? On the other hand, if you take, again, a point on the inside of the torus, you would get the sum of angles is smaller than that of a Euclidean triangle, right? But interestingly, what actually happens is, I think for people who are in, right, so an interesting way of constructing a torus is, I'm sure many of you have seen this picture, is basically to take a square and to identify these two sides, right? So if you identify this side with this, you would basically end up with a cylinder. And then what you're doing is you're taking the cylinder and identifying its circular caps, right? So that would give you a torus. Now this flat, this is a region in flat plane, right? So this clearly has a flat geometry. I don't want to use the word metric, but flat geometry. But on the other hand, when you are, unfortunately, when you're twisting, you actually end up, when you're twisting it into a cylinder, you still preserve the geometry by what we discussed. But unfortunately, when you have this additional twist, you actually destroy this flatness. Okay, so that means you can't faithfully represent a donut on a map. On the other hand, this is quite interesting that you can actually give a geometry to the torus. So give a geometry to the torus, which comes from this sort of square flat picture, which actually makes the torus completely flat. But unfortunately, you can't see that geometry in three-dimensional space. So this is actually a nice exercise if you want to think about it, that you cannot have a sort of closed surface in three-dimensional space, which has zero curvature everywhere. It has to then lie on a plane. You can't have any other surface. Okay, but it turns out that this flat torus, you can actually put inside four-dimensional space. And there are nice animations on YouTube for this. And this was actually a very famous theorem due to John Nash and independently due to Cooper. And this John Nash is the same famous Nash from Beautiful Mind. So this was one of his, amongst mathematicians, this was one of his more famous results, probably more famous than his game theory result. All right, I hope that answers the question.
Absolutely, sir. Thank you. And yet another question on similar lines. So you had mentioned earlier that the 2D map of a globe is not the best, as in the size of Greenland and Africa were treated the same, even though there was a considerable difference. So what is the best projection we have achieved so far of a globe on the plane? Can we do some sort of a cylindrical map or something?
Yeah, so I think the current projection is some sort of a cylindrical map. So I'm not an expert on that. But essentially, I think instead of preserving distances, I think it is more important to sort of preserve straight lines. Okay, so for instance, even if you take a sphere and you take the stereographic projection, it will basically send your sort of circles into straight lines. So what I'm saying is the following: you take a sphere and you take a sort of tangent plane at the North Pole. Or sorry, this is not the plane I want to consider. I want to take a plane that sort of cuts through the equator, right? And then from the North Pole, you can sort of start projecting everything down to this plane. And you can imagine that these straight lines are, these great circles go into straight lines, right? So that is advantageous because remember, these maps were actually made for navigation purposes, right? So for navigation purposes, you want to be careful that you keep directions same. Okay, so these are what are called as conformal maps. So you would ideally like a map that keeps these directions preserved. So I don't know if the current, I forget the name of the guy who is responsible for the current maps that we use. But one of the considerations was that one should be able to use them for navigation. And that was the primary consideration when you're, so distances aren't that important when you're navigating. But angles are, because you don't want to be lost in sea, right? Without knowing what direction to sail in. Okay, yeah.
And yet another question. So there have been quite a few questions. I'll ask a few to you now and probably like mail you the others. So that will make it a bit easier maybe. One of them is, what is the intuition behind the correction term appearing in the local Gauss-Bonnet?
Right. So yeah. So maybe let me. So there are two correction terms. So let me talk about the sort of angle turning term first, because that's, I think, easier to make sense of. The Gauss curvature term is notoriously difficult to make sense of, and in fact, unfortunately, there is no sort of intuitive proof of Gauss-Bonnet that doesn't require you to know a bit more advanced mathematics. So that's why, unfortunately, I couldn't prove or even give an outline of the proof of Gauss-Bonnet to you, because it's just difficult. It's hard. So let me make sense of at least the first correction term. So the idea is you have these curved triangles, right? So let me take sort of this thin triangle. And this is actually a good exercise that so you have these tangent directions, and then of course you change your tangent direction. Okay, so the total angle by which your tangent direction changes is basically this angle. Sorry. This angle that I called theta AB, right? So my triangle was, this is A, this is B, this is C. So I called this theta AB. Okay, so now you should, this is an exercise, I won't do it for you. You should try to, carefully trace out all the angles to actually prove that the external angles, if you take the sum, this will turn out to be precisely this. Okay, and remember, I'm taking, because these angles are turning in a clockwise direction, my thetas are actually negative. So you're subtracting some negative quantity, so you're effectively adding something to 2 pi. So this is an exercise, it's just Euclidean geometry. You should try to do it on your own. Now the question is, how do you actually calculate these turning angles locally by a local quantity? So that's where this integral of the geodesic curvature comes up, right? And so for that, the idea is locally you can approximate this curve as a circle, and you can draw what is called as an osculating circle, which is precisely tangential to the curve at that point. Okay, and the radius of that curve. So locally, when you're at this point, it's as if you're up to, a second order error. It's as if you're traveling on a circular track. And then for a circle, we measured this. This was basically 1 by the radius of the circle, right? So this is 1 by r, and then you should do right. So essentially, the what you're doing is that at each point you're drawing these oscillating circles, and you're computing the radius and taking the inverse of that radius and adding up those contributions as you go along. Right, so that will give you a correction term, and you have a correction term precisely because this velocity vector changes by the time you go to the endpoint. That's different from if you have a straight line, the velocity vector remains the same. So of course you will have to have some correction term, right? So of course, as I said, I don't know how to make sense of the Gauss curvature correction term. I don't know a way to say that so that you can understand it in 1 or 2 minutes. So I'm sorry about that.
So and yet quite a few more questions again. So in the exercise you had asked to prove the global Gauss-Bonnet. So is it true that every surface can be triangulated?
Yeah, that's an excellent question. That is true. And in fact, there is a certain dimension in which you cannot actually triangulate surfaces. I think I think as soon as you reach probably dimension 5 or something, you cannot. Of course, you have to make sense of what you mean by triangulation. So certain kinds of triangulations are still possible, but if you want certain triangulation with certain nicer properties, then beyond a certain dimension, you cannot do that. And this was actually and just to tell you how current the field is, this was actually a big breakthrough that was achieved earlier in this decade. So there's a mathematician at UCLA who proved this non-triangulation result. And I don't remember what the dimension is, but it's a certain, I think, not a particularly high dimension. It's either 4 or 5 or something.
Okay.
But in dimension 2, you can always triangulate. So you're on solid ground here, right? So yeah, that's an excellent question.
So yet another question. So is there a converse to the Euler formula? That is, if v plus f minus equals wholes, can we say something?
No. So again, this is sort of very standard in topology. So for people who have learned a bit of topology, you have all these invariants, and unfortunately, the invariants they'll only tell you. They'll only tell you how to distinguish things that are not the same. So if the invariants are equal, that actually doesn't tell you whether the two objects are the same or not topologically. But if the invariant is different, then you can point out that, okay, the objects cannot be the same. Okay, so this is sort of there throughout topology, and unfortunately, you can't do away with this. So if you do advanced if you at some point you take a course in topology, you will come across these very fancy objects called as fundamental groups, homology groups, and so on. So in fact, the Euler characteristic is actually related to the homology, to the dimensions of the homology group. And one of the first things you learn is that if two objects are the same, topologically, they have the same invariant, but the converse is not true, unfortunately. Okay.
Okay, so I think we can come to a close of this session. So once again, a huge thanks to Professor Ved for delivering this wonderful lecture. So
thanks. It was a pleasure. Yeah.
Thank you very much, sir. It's got quite a few students thinking. I still have a few doubts pending, so I'll write them to you in some time. So
sure, yeah.
And if any of you still have questions about the lecture, you can feel free to write to us at in the given mail ID tessellate.cmi@gmail.com. I'll put
actually, if people, sorry, just to interrupt, if people have questions, they could also write to me directly.
Okay.
You can also provide my IISc ID.
Okay, sure.
That's fine.
Okay, sure. Or I think it'll be easier if we'll compile the questions together and send it across.
Sure.
That would be a bit easier.
That's fine too. Yeah.
Sure. Yeah. So, or you can also leave your doubts under the comment section in YouTube, and they will be answered. So we formally come to a close of the session. So thank I thank all of you for attending. So to keep yourself updated with the latest developments and latest talks, so stay tuned to our official website, tessellate.cmi.ac.in, where you'll find other resources and the other scheduled talks. So see you all on Monday when Professor Abhay Ashtekar of Pennsylvania State University will be talking about black holes and their history, the work on which led to the 2020's Nobel Prize. So I hope to see all of you there. And once again, thank you very much, Professor Ved.
Thanks, Anirudh.
Thank you, sir. Have a good day.
Yeah, you too. Bye.
Bye, sir.